So looking at roots of multiplicity n, you should be able to do these first few examples without too much trouble. So I would pause the video and try these two. And you'll notice that the first one in part A is degree 2. And the basic idea there is if you take x minus 3, that quantity, and square it, remember that would mean x minus 3 times x minus 3. So if you were to FOIL that out or distribute there and multiply it out, you'd have x squared minus 6x plus 9, which is the degree 2 polynomial. So when you have these factors that repeat themselves, so here you have a 3, that means that you have x minus 3 times. So that would be an x to the third polynomial if you multiplied it out, so degree 3. Okay, so we see what happens here is you get x-intercepts that repeat themselves. For a y-intercept, remember you put 0 in for x. So you would do 0 minus 3 is negative 3, squared is positive 9, and negative 3 cubed is negative 27. Okay, so that's how you find the y-intercept. So the general sketch of these, with the x minus 3 squared, we have the vertex down here at 3, 0. And notice how it kind of bounces off that point. So you have your nice parabola there. And then the quantity x minus 3 cubed, that's your cubic graph, but just shifted to the right 3. And it goes through the point 3, 0, so it looks something like this. Now obviously these are not drawn to scale. These are just quick sketches. So we should notice that there's only one x-intercept for each function. However, h of x equals x minus 3 squared really means x minus 3 times x minus 3, which means that x equals 3 is a solution to the equation h of x equals 0 twice. So when that happens, we say that x equals 3 is a root of multiplicity 2. So how would you classify the roots of x minus 3 cubed? Well, you'd have x equals 3 as a root of multiplicity 3. And because x minus 3 times will give you x equals 3 times for an answer. So that would be a root of multiplicity 3. So how would you classify the roots of x minus 5 squared times x plus 4? Well, x equals 5 is a root of multiplicity 2, and x equals 4 will be multiplicity 1. Okay, so in general, if you were to look at explaining the behavior of x minus k to the n at the root when n is even. So if you did x minus k squared, x minus k to the 4th, to the 6th, to the 8th, and so on, what happens at the root? So I suggest in your calculator you graph some of those. So let me just, for example, let me graph y equals the quantity x minus 3, and I'll raise it to the 6th. So that would be n is even. Okay, so notice that gives me that basic U shape, and if I zoom in at the point 3, 0, so zoom in at the root, so I'll make it close to 3, and I'll zoom in. Oops. Sorry, I was up higher, sorry. So zoom 6. And then zoom in. There. Okay, notice what happens is we have that U shape coming down, and it comes very flat, but it hits right at that 3, 0 point. Okay, so what happens there is it looks like the function kind of bounces off at x equals 3. Okay, so f of x bounces off the x-axis at x equals k. And you can graph more functions like that if you want, as long as the exponent is even. What happens when the n value is odd? Okay, well, let me go back to zoom 6. So there's our standard window. Let me put in y equals x minus 3 to the 5th. Okay, so if I graph that, notice we get our basic cubic graph, or in this case a 5th exponent graph, x to the fifth, where it has that little bend in it. But notice what's happening is it's actually passing through that point. So if I zoom in, okay, notice it kind of flattens out there, and then it passes through the 0.30, and then it goes up higher and higher. So at the root, f of x passes through the x-axis at x equals k. Okay, notice how it passes through. If you have an x to the third or x to the fifth or x to the seventh, it'll pass through looking like this little shape here. It has that little curve in it. Okay, so in number 4, okay, we're going to look at the factor theorem and what we know about polynomials, like with end behavior and these multiple roots, and we're going to sketch a graph. So x minus 1 times x plus 3. What are the things we know here? We know the roots are 1 and negative 3. That's just setting the parentheses each equal to 0. We know that x equals 1 is multiplicity 1. X equals negative 3 is multiplicity 2 because of the squared. Remember that x minus 1, that's really to the first. So that's why it's multiplicity 1. The y-intercept we know is 0, negative 9. If you put 0 in for x, you have negative 1 times 3 squared, which will give you negative 9. We know we have a degree 3, so we have a 1 here, so that's degree 1, and then 2 more will be 3. So that's a degree 3. So if you were to multiply that all out, you would have x to the third plus blah, blah, blah. So we have opposite end behavior. So we know the x-intercepts, the y-intercept, we know opposite end behavior. If x is very large, so 100 minus 1 will be a large positive. 100 plus 3 is a large positive. Squared is even larger positive. So we have positive times positive, which is positive. So it's going up and to the right on the right-hand end. Put in a large negative, it'll go in the opposite direction here. Okay, so there is what the sketch of the graph will look like. Okay, and I'll show you, you can do the rest of these. I'll show you number B, or the second one. And then the last two, C and D. So here x squared, that means you have a root at 0. And that happens twice, so it bounces off there. And then x plus 6 and x minus 2 gives you negative 6 and positive 2. We know it's degree 4 because you have x squared, so there's 2, and then 3, 4. So we have x to the 4th if you were to multiply that out. And you can also put these in your calculator to see that it matches up. And again, these are not drawn to scale, so it's just a general basic shape that we're looking for. And the few things I do want to point out is when you are close to the root that you're looking at, notice how the function behaves. And this is one of the things I always found interesting when I was a student. If you look at the x squared, that gave you a root at 0, and notice how it's behaving like an x squared graph around 0, 0. The negative 6 and positive 2, those are multiplicity 1. Notice that it's cutting through those x-intercepts kind of almost as a line. Now it's not exactly a line, but it kind of passes like straight through. Okay, straight through. With x plus 2 to the third, notice how at negative 2, it looks like a cubic graph passing through right at negative 2. And then negative 4 has multiplicity 1. Notice how it just cuts right through negative 4, almost like a line would.